When the story of the Sun closes at the edge of its glowing atmosphere, the next step outward is not far. The first world we encounter is Mercury, a small, dark planet moving rapidly through fierce sunlight. Its speed led ancient observers to associate it with the swiftest messenger of the gods. It is the closest planet to the Sun, the smallest of the 8 planets, and one of the most extreme rocky worlds in the solar system. From Earth, Mercury is difficult to notice. It never travels far from the Sun in our sky, so it usually appears only briefly after sunset or before sunrise. The planet remains low near the horizon and is easily hidden by haze, buildings, mountains, or the brightness of twilight. Many people live their entire lives without realizing that they have ever seen Mercury, even though it is sometimes bright enough to be visible to the unaided eye. This difficulty of observation has helped shape Mercury's unusual reputation. Mars shines red in the middle of the night. Jupiter dominates the evening sky for months. Saturn can be followed through a telescope and recognized by its rings. Mercury, by contrast, appears only briefly, slips back into the glare of the Sun, and returns a few weeks later in another part of the twilight. It is nearby in distance, yet difficult to grasp in practice. Mercury's average distance from the Sun is about 58 million kilometers, or a little less than 4/10 of the distance between Earth and the Sun. Because its orbit is noticeably elliptical, that distance changes greatly. At its closest point, Mercury comes within roughly 46 million kilometers of the Sun. At its farthest, it travels out to about 70 million kilometers. This changing distance affects almost every aspect of the planet. Sunlight is far more intense when Mercury is near perihelion, the closest point in its orbit, than when it is near aphelion, the farthest point. The apparent size of the Sun also changes along the orbit. From Mercury's surface, the solar disk would appear roughly 2 to more than 3 times as wide as it does from Earth. The intensity of sunlight would also be several times greater. Mercury is not, however, the hottest planet. That title belongs to Venus, where a thick carbon dioxide atmosphere traps heat through an extreme greenhouse effect. Mercury has almost no atmosphere dense enough to retain warmth. Sunlit ground becomes intensely hot, but when a region enters darkness, heat escapes rapidly into space. Mercury needs only 88 Earth days to complete one orbit around the Sun. No planet travels around the Sun more quickly. Its average speed is about 47 kilometers per second. It moves faster near perihelion and more slowly as it approaches aphelion, following the same gravitational laws that govern objects moving on elliptical orbits. Mercury's speed impressed people long before the structure of the solar system was understood. The Romans named it after Mercury, the messenger god who moved swiftly between worlds. In Greek mythology, the corresponding figure was Hermes. Other cultures placed the planet within their own systems of calendars, astrology, navigation, or sacred meaning. Although their interpretations differed, they recognized the same basic feature. This point of light moved quickly and always remained close to the Sun. At first, its morning and evening appearances were not always recognized as the same celestial object. A bright point before sunrise was sometimes regarded as different from one seen after sunset. Over time, repeated observations showed that both belonged to the same wandering world. Mercury alternates between the morning and evening sky because its orbit lies inside Earth's orbit. By planetary standards, Mercury is very small. Its diameter is about 4,880 kilometers. It is only slightly larger than the Moon and less than half the diameter of Earth. If Earth were represented by a large orange, Mercury would be closer to the size of a small plum. Despite its small size, Mercury is a true planet rather than a moon or a dwarf planet. It is massive enough for gravity to pull its material into a nearly spherical shape. It travels directly around the Sun and has cleared most other large bodies from the region of its orbit. Mercury belongs to the terrestrial planets, the family of rocky worlds that also includes Venus, Earth, and Mars. The planet has no natural moon and no rings. No natural satellite has yet been discovered around Mercury. The region in which the planet could hold a companion through its gravity is relatively small because of the strong influence of the Sun, but the precise history that left Mercury without a moon remains unknown. The Mercurian sky therefore contains no large nearby world like Earth's moon. At night, stars and planets would cross a black sky without a bright satellite beside them. Gravity at Mercury's surface is about 38% as strong as gravity on Earth. A person with a mass of 70 kilograms would keep the same mass on Mercury, but would feel only about 38% as heavy as on Earth. Movement would be easier in some respects, yet the absence of breathable air, together with extreme temperatures and radiation, would make the surface immediately deadly without protection. Mercury's escape velocity is far lower than Earth's. This makes it difficult for the planet to retain light gases over billions of years, especially under the intense heating of the nearby Sun. Molecules and atoms released from the surface may be swept away by the solar wind, escape through thermal motion, or leave through other processes. The result is not a true atmosphere, but an extremely thin exosphere. The planet's density is unusually high. Earth is the densest planet overall because its greater mass compresses its interior more strongly. If the effect of self-compression is removed, Mercury is the densest rocky planet. Its mass is dominated by a very large metallic core, much larger in proportion to the planet than Earth's core is to Earth. This metallic interior is one of Mercury's central mysteries. The core extends through roughly 85% of the planet's radius, leaving a comparatively thin mantle and crust above it. In a simple cutaway view, Mercury would look less like a typical rocky planet with a moderate metal center, and more like an enormous iron-rich sphere covered by a relatively shallow rocky shell. Mercury's appearance from space is easy to misread. Its grey-brown surface, countless impact craters and broad plains make it resemble the Moon. The resemblance, however, is only superficial. Mercury has its own composition, volcanic history, magnetic field, and global network of cliffs formed as the planet cooled and contracted. Anyone approaching Mercury would see a world without oceans, clouds, forests, or weather systems. There would be no blue atmospheric rim and no changing bands of cloud. The surface would look ancient and completely exposed, preserving impact scars for billions of years because there is no rain, flowing water, thick atmosphere, or active system of plate tectonics to erase them quickly. The Sun would dominate the entire view. At Mercury's average distance, it takes only a little more than 3 minutes to arrive. Every bright surface, every long shadow, and every heated rock would be shaped by a star that appears far larger in the sky than the Sun does from Earth. Yet even under that fierce illumination, the landscape would remain mostly dark. Mercury has a low overall reflectivity, and its surface contains dark materials. Among them are carbon-rich components thought to be remnants of an ancient graphite crust. This low reflectivity surprised scientists because Mercury formed in a region once assumed to be hot enough to remove much volatile and carbon-rich material. Mercury is not simply a rock baked dry until only metal and silicate remained. Spacecraft data show that its surface still contains sulfur, potassium, sodium, chlorine, and more volatile elements than early models predicted. This discovery forced scientists to reconsider conditions in the inner solar system and the different paths by which the planet may have formed. Mercury's orbit also has the greatest eccentricity of the 8 planets. Its elongated shape changes the planet's speed and level of heating and helps create the unusual relationship between its rotation and its motion around the Sun. For many years, astronomers assumed that Mercury always kept one face toward the Sun, much as the Moon keeps one face toward Earth. This would have meant one hemisphere in permanent daylight and the other in permanent darkness. The assumption seemed reasonable because tidal forces tend to slow the rotation of bodies close to a larger object. Radar observations in the 20th century showed that this picture was wrong. Mercury rotates once every approximately 59 Earth days. Because it completes an orbit in 88 days, the two motions are locked in a 3-to-2 spin-orbit resonance. Mercury rotates exactly 3 times for every 2 trips around the Sun. This resonance is stable because Mercury's orbit is eccentric. The Sun's gravitational pull acts more strongly at certain points in the orbit, and over long periods it favors the 3-to-2 pattern. The planet is not frozen with one face toward the Sun, but its rotation and orbit are deeply linked. A solar day on Mercury, measured from one sunrise to the next, lasts 176 Earth days. That is twice the length of Mercury's year. A single cycle of daylight and darkness therefore lasts longer than 2 complete orbits around the Sun. The reason is that Mercury rotates slowly in the same direction that it travels around the Sun. After one rotation relative to the distant stars, the planet has moved far along its orbit, so it must turn much farther before the Sun returns to the same position in the sky. The result is an extraordinarily long day. At many places on Mercury, sunrise would be a gradual event. The Sun would climb slowly above the horizon and move across the black sky for weeks. Shadows would shorten at an almost imperceptible pace. The ground would heat for a very long time before evening finally approached. At certain longitudes, the motion in the sky becomes stranger still. Near perihelion, Mercury moves along its orbit so rapidly that its orbital motion briefly overtakes the apparent motion produced by rotation. From some regions of the surface, the Sun would rise, slow down, reverse direction, sink below the horizon, and then rise again. Elsewhere, near sunset, the sequence would occur in reverse. This double sunrise or double sunset does not mean that the Sun actually changes direction. It results from the combined geometry of Mercury's rotation and its changing orbital speed. The sky appears to hesitate as the planet passes through the fastest part of its elliptical orbit. Mercury's axial tilt is extremely small, only about 2 arc minutes, or nearly 0.034 degrees. Earth is tilted by more than 23 degrees, creating clear seasonal changes in the angle of sunlight and the length of daylight. Mercury stands almost upright relative to its orbital plane and therefore does not experience distinct seasons like those on Earth. This feature has an important consequence at both poles. Inside deep craters near the north and south poles, parts of the floor never receive direct sunlight. The crater walls block the sun even when the surrounding terrain is being intensely heated. These permanently shadowed regions are among the coldest places on the planet. The contrast is one of the great paradoxes of Mercury. A world closest to the Sun contains deposits of water ice. The ice survives not in open sunlight, but in dark polar traps where temperatures can remain low enough for frozen water to persist for very long periods. To understand how such a small planet came to possess a large metal core, a volcanic surface, a magnetic field, an exosphere, and hidden polar ice, we must look beyond its present appearance. Mercury is a record of the earliest solar system, of violent impacts, internal cooling, solar radiation, and the movement of materials between worlds. Mercury reminds us that distance from the Sun does not determine everything. Temperature also depends on atmosphere, rotation, surface properties, orbit, and the ability to retain heat. Internal activity is linked to composition and to the planet's cooling history. The world closest to the Sun is therefore not a simple opening chapter. It is small but dense, hot in sunlight but icy in shadow, ancient yet not completely inactive, and almost airless while still surrounded by a thin exosphere. Before descending to the cratered surface, it helps to return to the beginning, when Mercury did not yet exist as a planet. More than 4.5 billion years ago, the young Sun was surrounded by a rotating disk of gas, dust, metal, rock, and ice. Within that disk, countless grains began a long process of collision and accumulation. Near the young Sun, temperatures were high. Water ice and many volatile compounds could not easily condense in the hottest regions. Metals and heat-resistant minerals remained solid closer to the star, while large amounts of ice accumulated farther away. This broad pattern helped create rocky inner planets and volatile-rich outer worlds, but the details were far more complex than a simple temperature boundary. Dust grains collided and sometimes stuck together through electrostatic forces. Small clumps became larger aggregates. These grew into kilometer-scale planetesimals, then into planetary embryos large enough for gravity to dominate their encounters. Collisions became more energetic, and the inner solar system entered a long period of growth, destruction, mixing, and orbital change. Mercury probably formed from material spread across more than one narrow region. Gravitational interactions could move planetesimals inward and outward. Impacts could strip surface layers or deliver new compounds. The young Sun's radiation, magnetic activity, and solar wind also influenced the gas and small particles around it. One traditional explanation for Mercury's enormous core proposes that the young planet once possessed a thicker, rocky mantle. A gigantic collision may have removed much of the outer material while leaving the dense metal-rich interior behind. In this picture, Mercury is the surviving core of a once larger body. The impact hypothesis is possible, but it creates difficulties. A sufficiently violent collision would heat and vaporize large amounts of material. It might also remove volatile elements, yet Mercury's surface contains more sulfur, potassium, and other volatile substances than expected. Any successful model must explain both the metal-rich interior and the survival or later delivery of volatile material. Another group of models focuses on conditions in the solar nebula. Chemical reactions close to the young Sun may have favored metal-rich solids. Aerodynamic processes could have separated metal grains from silicate grains. Magnetic forces might also have concentrated iron-bearing particles in certain regions of the disk. A third possibility involves repeated impacts rather than one single catastrophe. Numerous high-energy collisions could gradually remove parts of the rocky exterior. This process would not need to happen all at once, but it would still have to preserve the chemical signatures measured at the surface. Modern models do not necessarily treat these possible formation paths as mutually exclusive. Mercury is probably the result of unusual starting material, the thermal and chemical environment near the Sun, orbital migration, and many collisions. Bepi Colombo and future missions will test these ideas through improved measurements of composition, gravity, topography, and magnetic structure. As the growing planet accumulated mass, gravitational energy, impacts, and radioactive decay heated its interior. Dense metal sank toward the center, while lighter silicate rock rose above it. This process of differentiation produced a metallic core, a rocky mantle, and a crust. The core likely contains mostly iron, with lighter elements such as sulfur and perhaps silicon mixed into it. These lighter elements lower the melting temperature and help part of the core remain liquid even in a small planet that has been cooling for billions of years. Above the core lies a mantle far thinner than Earth's in proportion to the planet. The outer, rocky shell, including mantle and crust, is only a few hundred kilometers thick. This thin shell strongly affects Mercury's geology because large structures can reflect changes occurring deep within the interior. The earliest surface was repeatedly destroyed by impacts, large planetesimals struck with enough energy to melt broad regions, excavate deep basins, and spread debris across enormous distances. Smaller impacts continued after the largest bodies were gone. The cratered landscape visible today is the surviving record of this long bombardment. At the same time, the interior released heat through volcanism. Molten rock rose through fractures and spread across low areas. Some lava flows filled older craters and created smooth plains. Other eruptions were explosive, throwing material outward from vents and leaving bright or reddish deposits visible in enhanced color spacecraft images. Mercury's geological history cannot be read from a single image. The relative ages of surfaces must be reconstructed from overlapping craters, volcanic plains, fault scarps, ejecta deposits, and changes in composition. Each feature represents an event, but those events accumulated over billions of years. The oldest surviving terrains are densely covered with craters of many sizes. When one crater cuts across another, the younger structure can be identified. When smooth plains cover a crater floor or bury older features, volcanism must have occurred after the impacts. By mapping these relationships across the planet, scientists build a sequence of geological periods. Mercury's surface preserves evidence of an early crust, different from the crusts of Earth, the Moon, and Mars. The Mercury surface, space environment, geochemistry, and ranging spacecraft data suggest that carbon may have been concentrated near the surface of the young planet. One hypothesis proposes that a global magma ocean cooled and allowed graphite, which is less dense than many silicate minerals, to float upward and form an ancient primary crust. Later impacts would have broken and mixed this graphite-rich layer into the surface. Dark material excavated by craters may contain remnants of that early crust. If this interpretation is correct, some of the dim color seen across Mercury comes from carbon formed during the planet's earliest differentiation. A graphite flotation crust would be a remarkable contrast with the Moon, where light plagioclase minerals floated to form much of the ancient highland crust. Two small, airless worlds could therefore have produced very different first surfaces because their chemical compositions were not the same. Mercury's low iron abundance at the surface is also surprising. The planet has an enormous iron-rich core, yet the silicate crust is relatively poor in oxidized iron. This suggests that Mercury formed under strongly reducing chemical conditions, where oxygen was less available to combine with metals. Under such conditions, elements behave differently from the way they do in many Earth rocks. Sulfur can enter minerals and metal in unusual proportions. The surface may contain compounds rare on Earth. Understanding this chemistry is essential for interpreting infrared and X-ray measurements from orbit. By the time the largest early impacts became less common, Mercury had already become a differentiated planet with a thick metal center and a volcanic exterior. But the interior was still changing. As heat escaped, the core and mantle cooled, the entire planet slowly contracted. This contraction created one of Mercury's most distinctive landscapes, long curved cliffs often called Lobat scarps. They can extend for hundreds of kilometers and rise more than a kilometer above the surrounding terrain. They are the surface expression of thrust faults where one section of crust has been pushed over a neighboring section. The process can be imagined as the skin of a fruit adjusting when the interior shrinks slightly while the outer layer remains rigid. The crust must accommodate a smaller interior. On Mercury, it fractured and overlapped along faults, forming scarps that cut across plains, craters, and older landscapes. Because some scarps cut relatively young features, contraction continued long after the earliest geological period. Small scarps identified in high-resolution images may indicate that the planet has continued to shrink geologically recently. Mercury is not tectonically active in the same way as Earth, but its crust has not been completely motionless. Measurements of Mercury's total contraction have changed as mapping improved. Early estimates based on limited Mariner 10 coverage were modest. Global, the Mercury surface, space environment, geochemistry, and ranging spacecraft data revealed many more scarps and suggested a radius decrease of several kilometers over the planet's history. Even a few kilometers of global shrinkage is significant. It records the cooling of a core that occupies most of the planet. The cliffs therefore connect surface geology directly to the thermal evolution of the interior. Mercury lacks Earth-like plate tectonics. Its crust is not divided into large mobile plates that continually create ocean basins, build mountain chains, and recycle material into the mantle. Instead, its global tectonic pattern is dominated by contraction, impact deformation, and local stresses. Yet the absence of plate tectonics does not mean the surface is simple. Impact basins created rings of faults and fractures. Lava flooded broad regions. Explosive eruptions opened vents. Cooling produced thrust faults. The gravity of large structures altered nearby crust. Mercury's landscape is a layered result of different forces acting over immense time. The largest and most famous impact structure is the Caloris Basin. It is about 1,550 kilometers across, nearly one-third the diameter of Mercury. The asteroid or comet that created it released energy on a planetary scale. The collision excavated an enormous cavity and surrounded it with rings of mountains and fractured terrain. Ejecta spread across large regions. Later volcanic plains filled much of the basin's interior, creating a smoother floor marked by younger craters and tectonic features. Near the center of Caloris lies a complex system of troughs known informally as the Spider, centered on Apollodorus crater. The troughs radiate outward in many directions, while the crater itself is slightly offset. Their origin may involve uplift, volcanic activity, or stresses created as the basin floor changed after impact. On the side of Mercury opposite Caloris is a region of chaotic terrain. Seismic waves from the giant impact may have traveled through the planet and focused near the antipode, breaking the crust into blocks and hills. Some details remain debated, but the global connection illustrates how a single collision can affect an entire small planet. Other large basins include Rembrandt and Rachmaninoff. Their floors preserve volcanic plains, faults, and variations in color and composition. Each basin is both a scar from impact and a natural window into deeper crustal material. Crater rays spread across Mercury from relatively young impacts. These bright streaks consist of crushed and excavated material deposited outward from a crater. Over time, exposure to micrometeorites and solar radiation darkens and alters the surface, so prominent rays usually indicate a geologically young crater. Space weathering on Mercury differs from space weathering on the Moon. The planet is exposed to stronger solar radiation, higher temperatures, and a more intense solar wind. Micrometeorites also strike at high speeds. These conditions change the optical properties and chemistry of surface grains. The regolith, a layer of broken rock and dust, covers much of the surface. It is produced by billions of years of impacts ranging from microscopic particles to large asteroids. Without wind or rain, footprints or disturbances would not be quickly erased, but constant small impacts would gradually churn and modify the soil. Mercury's colors are subtle to human eyes. Natural color images show a mostly dark, gray-brown world. Enhanced color maps reveal differences connected with volcanic units, impact ejecta, low reflectance material, and unusual hollows. These colors are scientific tools rather than the appearance a person would see directly. Among the most unexpected features discovered by the Mercury surface, space environment, geochemistry, and ranging spacecraft are hollows. They are shallow, irregular depressions with bright interiors and halos, often found on crater floors, central peaks, and areas where deeper material has been exposed. Hollows do not look like ordinary impact craters. They often have no raised rims and can occur in clusters that resemble areas where material has been removed. Many appear relatively fresh with sharp boundaries and little accumulation of small craters. The leading explanation is that volatile-bearing minerals become unstable when exposed at the surface. Heat, solar radiation, and vacuum gradually remove part of the material, leaving depressions behind. The responsible compound has not yet been identified. The hollows show that volatile substances are found not only in polar cold traps, but also within rocks at lower latitudes. The chemistry of the crust is therefore more complex than the image of a world baked completely dry. Some hollows appear to be developing even in the present era, although their rate of change is extremely slow by human standards. If material loss is continuing, Mercury possesses a surface-altering process driven by sunlight and vacuum rather than by wind or water. Irregular pits surrounded by bright material also reveal a history of explosive volcanism. Gas dissolved in magma probably expanded rapidly near the surface and scattered fine material across the landscape. Explosive volcanism requires magma containing dissolved gas. This evidence complements elemental measurements and shows that Mercury did not lose every volatile substance during formation. Smooth plains covering much of the northern hemisphere and other low regions were formed mainly by lava, impact melt, or a combination of both. Mercury's volcanic history is therefore not identical to the basaltic maria of the Moon. The northern volcanic plains are among the largest young volcanic provinces on the planet. Their surfaces contain fewer large craters than ancient terrains, indicating later formation. Wrinkle ridges and ghost craters reveal deformation and buried structures beneath the lava. Mercury's volcanic activity eventually declined as the interior cooled and the outer shell thickened. Magma had greater difficulty reaching the surface. Global contraction may also have closed pathways. Yet the timing of the final eruptions remains an active question, and some volcanic deposits appear younger than early models expected. Mercury's geological history did not unfold in one short episode, followed by complete silence. Impacts, volcanism, contraction, and space weathering overlapped across billions of years, so each region reached its present form at a different time. To reconstruct that sequence, scientists combine images, crater counts, topographic maps, spectroscopy, gravity measurements, and magnetic measurements. Each kind of evidence reveals only part of the story. Mercury is small enough that it is easy to imagine it cooled completely long ago. The Moon lost its global magnetic field early, while Mars today mainly preserves magnetism in its crust rather than a strong global dynamo. Mercury, however, still generates an intrinsic magnetic field. Mariner 10 discovered it in the 1970s, and the Mercury surface, space environment, geochemistry, and ranging spacecraft later confirmed it in far greater detail. The field is weaker than Earth's, but it is clearly global and generated inside the planet rather than merely induced by the solar wind. The existence of the field implies that at least part of Mercury's metallic core remains liquid and moving. A dynamo requires electrically conducting fluid, energy to drive motion, and planetary rotation. Understanding how this operates in a small, slowly rotating planet is one of the major goals of Mercury science. Mercury's core may contain a solid inner region surrounded by a liquid outer layer. Although its exact structure is uncertain, sulfur or other light elements lower the melting point and help preserve liquid metal. Heat released by core solidification may drive convection. Another possible energy source is compositional buoyancy. As iron solidifies, lighter elements may be excluded into the remaining liquid, producing motion. The balance between thermal and chemical convection determines how the dynamo evolves. The magnetic field is unusual because its dipole is shifted northward from the planet's center. The Mercury surface, space environment, geochemistry, and ranging spacecraft measurements showed that the magnetic equator lies north of the geographic equator. This offset creates different magnetic conditions in the northern and southern hemispheres. At the surface, the field is only about 1% as strong as Earth's. The nearby solar wind can compress Mercury's magnetosphere strongly, sometimes pushing the boundary close to the planet. Under extreme conditions, solar particles can gain direct access to broad regions of the surface. Mercury's magnetosphere is therefore small, dynamic, and strongly controlled by the Sun. It has a bow shock where the solar wind slows, a magnetopause separating solar and planetary magnetic fields, and a long magnetotail extending away from the Sun. Magnetic reconnection occurs when field lines carried by the solar wind connect with Mercury's field. This process transfers energy and plasma into the magnetosphere. Because the solar wind is stronger near Mercury than near Earth, changes can occur rapidly. The magnetotail can store energy and release it through substorm-like events. Mercury's magnetosphere resembles Earth's in some broad, physical processes, but it operates on a much smaller scale and in a more intense solar environment. Events that take hours at Earth may unfold in minutes at Mercury. The interaction between the magnetosphere and surface contributes to Mercury's exosphere. Solar wind ions can strike the ground and knock atoms loose. Micrometeorite impacts vaporize tiny amounts of rock. Heating can release atoms from minerals, and photons can eject particles through processes such as photon-stimulated desorption. The exosphere is so thin that its atoms rarely collide with one another. It is not an atmosphere in the familiar sense. There is no air pressure a person could feel, no wind, no clouds, and no blanket to carry heat from day to night. Detected exospheric species include sodium, potassium, calcium, magnesium, hydrogen, helium, and oxygen. Different elements respond to different release processes and vary with time, position, local temperature, and solar activity. Sodium is especially visible because it scatters sunlight efficiently. Observations reveal a long sodium tail extending away from the Sun, somewhat like the ion or dust tail of a comet. Mercury is a planet, but in this respect it can temporarily display a faint, comet-like feature. The exosphere is constantly being renewed and lost. Atoms rise in ballistic arcs, fall back to the surface, become ionized, or escape into space. The surface and space environment are connected in a continuous cycle. Because Mercury has almost no atmosphere, the sky would remain black even at midday. The Sun would blaze in darkness, and stars might remain visible if the glare could be blocked. There would be no blue scattering, no red sunset produced by thick air, and no gradual twilight like the ones seen on Earth. Shadows would be extremely sharp. A rock in sunlight might be heated intensely on one side, while the side in shadow remained far colder. Heat would travel through the rock by conduction, but almost no surrounding gas would be present to distribute it. Near the equator, daytime surface temperatures rise to about 430 degrees Celsius. During the long night, temperatures fall to nearly -180 degrees Celsius. This range is among the greatest found on any planet. The exact temperature depends on latitude, local time, surface properties, topography, and Mercury's changing distance from the Sun. Near perihelion, regions receiving direct sunlight experience stronger heating. Slopes facing the Sun can become hotter than nearby shaded ground. A human-built machine on Mercury would need to survive not only high temperature, but enormous changes across the day-night cycle. Materials would expand and contract. Electronics would require shielding and thermal control. Solar panels would receive abundant energy but could overheat. The poles provide a completely different environment. Because Mercury's axis is nearly upright, sunlight always arrives at a low angle near the poles. Deep crater floors remain permanently hidden, from direct illumination. Radar observations from Earth first revealed bright patches near the poles that behaved like deposits of water ice. The Mercury surface, space environment, geochemistry, and ranging spacecraft later mapped these regions, measured their temperatures, and provided strong evidence that the radar bright material is dominated by frozen water. Some deposits are exposed at the surface. Others lie beneath a thin layer of dark, insulating material, possibly rich in organic compounds delivered by asteroids and comets. This cover protects the ice where temperatures are slightly too warm for long-term exposure. The amount of polar ice is small compared with Earth's oceans, but scientifically important. It shows that water can be delivered, transported, trapped, and preserved even on the closest planet to the Sun. Possible sources include impacts by comets and water-rich asteroids, chemical reactions involving the solar wind, and material released from Mercury's interior. Once water molecules reach the surface, they can hop across the planet through repeated heating and recondensation until some enter permanent cold traps. Most molecules would be destroyed or escape before reaching a pole. A small fraction would survive. Over billions of years, this gradual process could build the deposits observed today. Mercury's polar regions are therefore archives of material delivered through the inner solar system. The ice may contain clues about the types of objects that struck Mercury and the chemical history of water and organic compounds near the Sun. These deposits also demonstrate how local geography can overcome a planet's average environment. Mercury is close to the Sun, but sunlight cannot reach every surface. A deep shadow can remain colder than places much farther from the star. The presence of ice does not make Mercury habitable in any ordinary sense. There is no stable liquid water at the surface, no protective atmosphere, and intense radiation reaches the ground. The ice is trapped in darkness at temperatures far below freezing. Even so, Mercury expands our understanding of where water can exist. Water in the solar system is not limited to blue planets and icy moons. It can survive in protected niches on airless bodies, inside minerals, beneath soil, and within permanent shadow. The search for polar ice was one of the Mercury surface, space environment, geochemistry, and ranging spacecraft's great successes, but it also left new questions. How pure are the deposits? How thick are they? When were they delivered? Do the North and South poles contain different mixtures? Are organics present in measurable amounts? Bepi Colombo will study the polar regions with instruments designed to improve maps of composition, topography, temperature, and neutron signals. Its orbit will provide new viewing geometries and complementary measurements from 2 spacecraft. Before reaching that modern mission, however, Mercury passed through centuries of changing human understanding. It began as a wandering point of light, became a planet in geometric models, later served as a test of gravity, and finally emerged as a physical world explored by machines. Because Mercury always remains close to the Sun in the sky, telescopic observation has long been difficult. Atmospheric turbulence is often strongest near the horizon where the planet appears. Daytime observation is possible, but it demands great care because pointing equipment too close to the Sun can be dangerous. The earliest telescopes showed that Mercury has phases like the Moon. It can appear as a crescent, half illuminated or nearly full, depending on the relative positions of the planet, Earth, and the Sun. These phases strengthened the understanding that Mercury travels around the Sun inside Earth's orbit. A complete cycle of Mercury's phases is connected to its synodic period, the time required for the planet to return to the same relative position with Earth and the Sun. This interval lasts nearly 116 Earth days. During inferior conjunction, Mercury passes between Earth and the Sun. Its orbital plane is tilted by about 7 degrees relative to the ecliptic, so the planet usually passes slightly above or below the solar disk. Only on rare occasions is the alignment precise enough for Mercury to cross in front of the Sun in an event called a transit. The planet then appears as a small black dot moving slowly across the bright solar disk. A transit must be observed with a proper solar filter, or by projection. Looking directly at the Sun through an unfiltered telescope can cause permanent eye damage. Transits of Mercury helped astronomers test predictions of planetary motion and improve measurements of the solar system. They also provided opportunities to study the black drop effect and refine methods later applied to transits of Venus and exoplanets. Mercury's orbit played a central role in the development of modern physics. According to Newtonian gravity, the point of closest approach to the Sun, the perihelion, should slowly shift because of the gravitational pulls of other planets. Most of the observed precession had been explained, but a small excess remained. Astronomers proposed several causes, including an unseen planet inside Mercury's orbit. This hypothetical world was sometimes called Vulcan. Repeated searches failed to find it. The unexplained motion remained until Albert Einstein developed the general theory of relativity. In Einstein's theory, gravity is not merely a force acting across space. Mass and energy curve spacetime, and objects move along paths within that curved geometry. The curvature is especially important close to a massive body. General relativity predicted exactly the additional precession observed in Mercury's orbit. The planet became one of the first great tests of the new theory. Mercury continues to test gravity today. Precise radio tracking of spacecraft can measure its orbit and rotational behavior with extraordinary accuracy. These data constrain the Sun's shape, the distribution of mass in the solar system, and possible deviations from general relativity. Mercury also undergoes physical libration, a small rocking motion in its rotation. Measuring this movement helped show that at least part of the planet's core remains liquid. If the entire planet were a single rigid body, its response to the torque of the Sun would be different. Radar observations from Earth were crucial in discovering the 59-day rotation period. Before those measurements, the mistaken idea of synchronous rotation persisted for decades. This reminds us that even a nearby planet can conceal basic properties until technology becomes sensitive enough to reveal them. Before spacecraft produced photographs, astronomers tried to map Mercury through telescopes on Earth. The work was difficult because the planet is small, usually low in the sky, and viewed through turbulent air. Features appeared and disappeared as atmospheric distortion changed from moment to moment. Observers often drew dark patches and bright regions, then compared sketches made on different nights. The drawings did not always agree. Some features reflected real differences in brightness. Others arose from poor observing conditions, optical limits, or the tendency of the human eye to connect faint marks into familiar shapes. In the 19th century, Giovanni Schiaparelli studied Mercury and concluded that it rotated once during each orbit, always keeping the same face toward the Sun. Later, Eugene Antoniadi supported a similar view and produced influential maps with named markings. The synchronous rotation model shaped imagined descriptions of Mercury for many years. One hemisphere was pictured as an eternal furnace, the opposite hemisphere as a world of permanent night, and a narrow twilight zone between them as the only region with moderate temperatures. Writers and scientists speculated about settlements along that twilight belt, where the Sun might remain near the horizon. These ideas were reasonable within the accepted model, but the model itself was wrong. Radar changed the picture in 1965. Powerful radio signals were transmitted toward Mercury, reflected from the surface, and received back on Earth. The frequency shift across the rotating planet revealed a period of about 59 days. The result was unexpected. Mercury was not synchronously locked. Its 3-to-2 resonance meant that every region eventually experienced both daylight and darkness, although each solar day remained extraordinarily long. This discovery transformed the planet before any spacecraft arrived. The permanent hot side and permanent cold side disappeared from scientific descriptions. In their place came a world with slow-moving sunlight, large temperature cycles, and the possibility of double sunrises. Radar later revealed more than rotation. By sending signals toward Mercury's poles, astronomers detected unusually bright reflections inside craters. The radar properties resembled those of water ice, beginning a debate that the Mercury surface, space environment, geochemistry, and ranging spacecraft would later resolve with orbital measurements. Ground-based radar also mapped broad surface features when optical telescopes could not. The most detailed radar images identified craters, plains, and rough terrain at wavelengths capable of penetrating some surface dust. Modern observatories continue to study Mercury from Earth. Optical telescopes measure reflected light and exospheric sodium. Radio telescopes refine rotation and surface properties. Solar observatories record transits. These measurements complement spacecraft rather than becoming unnecessary after exploration begins. The naming of Mercury's landscape follows international conventions managed by the International Astronomical Union. Large craters are generally named after deceased artists, musicians, painters, writers, and other contributors to culture. The result is a map where names from many centuries and regions share the same planet. Beethoven, Shakespeare, Tolstoy, Rembrandt, Rachmaninoff, Matisse, and many others appear across the cratered surface. The convention gives Mercury a distinctive cultural geography. A barren landscape carries reminders of music, literature, dance, painting, and architecture created on Earth. The names do not describe the physical origin of the craters, but they help scientists communicate clearly about location. Other types of features follow different themes. Cliffs, called rupees in planetary nomenclature, are named after ships of discovery and exploration. Valleys and plains use their own naming systems. The formal vocabulary allows global maps produced by different teams to remain consistent. Mercury's prime meridian, the 0-degree reference for longitude, is tied to a small crater named Hun Kal. The name means 20 in a Maya language, and the crater was chosen because it lies near 20 degrees west longitude in the older coordinate system. A precise coordinate system matters because Mercury's rotation is not perfectly uniform. Solar gravity produces librations, and the planet's orientation must be modeled carefully. Spacecraft images, altimetry, and radio measurements all need to be placed on the same reference frame. The Mercury surface, space environment, geochemistry, and ranging spacecraft improved this frame by mapping the globe and measuring topography. Bepi Colombo will refine it further. Small changes in Mercury's rotation contain information about the state of the core and the way the mantle and crust respond to solar torque. Topography reveals a planet with broad elevation differences. Some basins lie several kilometers below surrounding terrain, while highlands rise above the average radius. The northern lowlands contain extensive volcanic plains, and the southern hemisphere includes rugged, ancient regions. Mercury's highest and lowest points are not shaped by oceans or plate boundaries. They reflect impact excavation, volcanic filling, crustal deformation, and the distribution of mass within the planet. The gravity field adds information that topography alone cannot provide. A high region does not always produce a corresponding positive gravity anomaly because crustal thickness and deep structure also matter. Comparing topography with gravity allows scientists to estimate how fully large basins are compensated. If a basin is not fully compensated, the lithosphere must once have been strong and rigid enough to support the load when the structure formed. The gravity field therefore preserves evidence of the planet's ancient thermal state. At Caloris, topographic and gravity data show that the basin floor responded through several stages to volcanic loading, cooling, and global stress. Some regions were stretched, while others were compressed. Rachmaninoff and Rembrandt also preserve different patterns of deformation. Comparing these basins helps reveal how Mercury's thin crust supports mass and adjusts after enormous impacts. Some craters contain central peaks that lift material from depth. Spectrometers can examine these peaks to infer the composition of layers otherwise hidden beneath the surface. An impact, therefore, destroys part of the crust while also exposing a sample of the interior. Bright crater rays slowly fade under space weathering. Their disappearance provides a relative clock, although the rate is not simple. Solar wind intensity, micrometeorite bombardment, composition, and local temperature all influence how quickly fresh material darkens. Crater counting is another relative clock. A surface with many large overlapping craters is usually older than a smooth surface with fewer craters, but the method depends on models of impact rates and must account for secondary craters formed by debris from a larger collision. Absolute ages are difficult because no Mercury rock has been returned to Earth and dated in a laboratory. Scientists calibrate crater chronologies using the Moon and dynamical models, but uncertainty remains. A sample return mission would transform the geological timeline. Mercury's oldest terrains are associated with intense bombardment and plains lying between densely packed craters. Later stages saw the formation of large basins, widespread lava flows followed by decline, and continuing tectonic deformation. The planet did not change everywhere at once. One region preserves early crust, another is covered by lava, and another exposes deep material through a younger impact. Geological periods are therefore only a framework for many overlapping regional histories. Ejecta from large impacts also formed chains of secondary craters extending far from their source basins, complicating crater counts. Volcanic pits must also be distinguished from hollows. Volcanic pits are generally larger and accompanied by eruptive deposits, while hollows are shallow depressions formed as material is lost. Shape, color, geological setting, and composition help distinguish the two kinds of structure. Alongside compressional scarps, Mercury has extensional troughs, especially inside large impact basins. There, uplift of the basin floor, cooling, and volcanic loading create local stresses that oppose the global tendency toward contraction. Thermal models must reproduce the observed contraction, the duration of volcanism, and the magnetic field that still exists today. If the interior cools too rapidly, volcanism ends too early and the core is more likely to freeze, contradicting the magnetic field that still exists. If cooling is too slow, the model fails to produce enough of the contraction recorded at the surface. These limits show that the thin mantle and enormous core control much of Mercury's heat transfer. Convection in the rock was probably far more restricted than in Earth's thick mantle. Mercury's proximity to the Sun also affects telescopic and spacecraft measurements. The bright surface reaches high temperatures, instruments receive intense infrared radiation, and solar pressure acts strongly on spacecraft. Calibration must account for conditions that change with distance and local time. Images taken near the terminator, the boundary between day and night, reveal relief through long shadows. Images taken near noon show color and albedo more clearly, but flatten the appearance of topography. Combining lighting conditions creates a fuller geological map. The terminator itself moves slowly across Mercury. A spacecraft in polar orbit can pass over regions at different local times over the mission, gradually observing how temperature, exosphere, and illumination change. Bepi-Colombo's two orbiters will not remain side by side. Their different paths are designed to sample complementary regions. At times, one can measure the upstream solar wind, while the other measures the response closer to the planet. This arrangement may clarify whether a sudden magnetospheric change was triggered by the Sun or generated internally within the magnetotail. The distinction is difficult when only one spacecraft is present. The mission will also improve measurements of Mercury's tidal response. The Sun raises small tides in the solid planet. The amplitude depends on internal layering, and the rigidity of the mantle and core. Precise tracking can determine parameters related to these tides and to rotation. Together with gravity and magnetic data, they will help estimate the size of the inner core and the depth of liquid layers. Mercury is therefore measured through motion as well as images. Tiny variations in a spacecraft's radio signal reveal gravity. Small shifts in the planet's orientation reveal the core. Weak spectral lines reveal atoms in the exosphere. The physical world emerges from changes that human senses could never detect directly. Within only a few generations, uncertain telescopic sketches were replaced by global geophysical maps. Even so, knowing where a cliff stands is not the same as knowing when it formed, how deeply its fault extends, or whether it remains active. Mariner 10, the Mercury surface, space environment, geochemistry, and ranging spacecraft, and Bepi Colombo observed or will observe Mercury during different phases of solar activity. Comparing data across decades will help scientists search for long-term changes in the exosphere, magnetic field, and surface. Mercury's short orbit continually carries it through changing conditions in space. The solar wind strengthens and weakens, dust streams vary, and the Sun itself moves through its activity cycle. The planet therefore resembles a repeating experiment with constantly changing inputs. The first spacecraft to reach it was Mariner 10. Launched in 1973, the spacecraft used a gravity assist at Venus, and then flew past Mercury 3 times in 1974 and 1975. Mariner 10 was the first spacecraft to use a planetary gravity assist to reach another planet. By passing Venus, it changed speed and direction without using an impossible amount of fuel. This technique became essential for later missions throughout the solar system. The spacecraft photographed about 45% of Mercury's surface. Because the flybys occurred with similar lighting and geometry, the same hemisphere was repeatedly visible. Large areas remained unseen. Mariner 10 discovered Mercury's magnetic field, measured its thin exosphere, and revealed a cratered surface crossed by enormous scarps. The Caloris Basin was partly imaged, though portions near the day-night boundary were difficult to interpret. After Mariner 10, Mercury waited more than 3 decades for another close visitor. The delay was not caused by lack of interest alone. Reaching and orbiting Mercury is unexpectedly difficult. A spacecraft leaving Earth already moves around the Sun at nearly Earth's orbital speed. To reach Mercury, it must lose a large amount of orbital energy. Falling inward increases speed, so the spacecraft arrives near Mercury, moving rapidly relative to the small planet. Mercury's gravity is not strong enough to capture a fast spacecraft easily. Without careful trajectory design, a probe would fly past or require an enormous braking maneuver. The nearby Sun also creates intense heat and radiation that spacecraft must survive. The Mercury surface, space environment, geochemistry, and ranging mission of the National Aeronautics and Space Administration solved the problem through a long journey. The spacecraft made 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself. Launched in 2004, it took more than 6 years to enter orbit around Mercury in March 2011. Its full mission name described the study of Mercury's surface, space environment, geochemistry, and ranging. Its instruments included cameras, spectrometers, a magnetometer, a laser altimeter, particle detectors, and a radio science system. The orbit of the Mercury surface, space environment, geochemistry, and ranging spacecraft was highly elliptical. It passed close above the northern hemisphere and traveled far from the planet in the south. This arrangement limited heating and allowed several kinds of observation, although topographic coverage was better in the north. During more than 4 years in orbit, the spacecraft mapped the entire planet and measured elemental composition. It studied the magnetic field and magnetosphere, discovered hollows, confirmed widespread volcanism, and demonstrated that the material at the poles is dominated by water ice. It also showed that Mercury's surface contains unexpectedly high abundances of volatile elements. These findings weakened simple formation models based on extreme heating or complete mantle stripping. Laser altimetry mapped mountains, plains, basins, and polar craters. Radio tracking revealed the gravity field and helped constrain the internal structure. Measurements of libration supported the presence of a liquid outer core. The Mercury surface, space environment, geochemistry, and ranging spacecraft detected the northward offset of the magnetic field and observed rapid magnetospheric dynamics. It watched solar wind particles enter, saw sodium and other atoms in the exosphere, and measured how the environment changed with Mercury's orbit and solar activity. The mission lasted far longer than its original primary phase. Engineers used creative maneuvers to maintain the orbit as fuel declined. Eventually, the spacecraft could no longer raise its altitude. On April 30, 2015, the Mercury surface, space environment, geochemistry, and ranging spacecraft struck Mercury's surface at high speed, creating a small, new crater. The impact ended the mission, but the data remain active sources of research. A spacecraft becoming part of the world it studied is a quiet ending. The Mercury surface, space environment, geochemistry, and ranging spacecraft's instruments stopped, yet its maps and measurements transformed Mercury from a partly known crescent into a globally explored planet. Still, one orbiter could not answer every question. Its orbit favored the north. Some instruments lacked the resolution or wavelength coverage needed for detailed mineral mapping. The magnetosphere changes so quickly that simultaneous measurements at more than one location are valuable. The next mission was designed to be more ambitious. Bepi-Colombo is a joint project of the European Space Agency and the Japan Aerospace Exploration Agency. It carries two scientific orbiters to study Mercury at the same time. The mission is named after Giuseppe Colombo, an Italian mathematician and engineer whose work helped explain Mercury's 3:2 spin-orbit resonance and contributed to the trajectory design of Mariner 10. Bepi-Colombo launched in October 2018 on an Ariane 5 rocket. Its journey required an Earth flyby, 2 Venus flybys, 6 Mercury flybys, long arcs of solar electric propulsion, and years of careful navigation through the inner solar system. The spacecraft traveled as a combined stack. The Mercury transfer module provided electric propulsion and large solar arrays during the cruise. The European Mercury Planetary Orbiter carries instruments focused on the surface, interior, composition, exosphere, and magnetic environment. The Japanese orbiter MIO, originally called the Mercury Magnetospheric Orbiter, is designed to study magnetic fields, plasma, energetic particles, waves, and the structure of the magnetosphere. Its spinning design and heat control systems help it survive the harsh environment. A protective structure called the Magnetospheric Orbiter Sunshield and Interface Structure shielded MIO during the journey and arrival operations. Once captured into Mercury orbit, the components will separate and move into different polar orbits. The European Mercury Planetary Orbiter will travel in a lower polar orbit suited to mapping the surface and measuring gravity, topography, composition, and the magnetic field. MIO will use a more elongated polar orbit to sample the magnetosphere over a broad range of distances. Observing with 2 spacecraft at once is important. A single probe cannot always distinguish a change moving through space from a change occurring over time. 2 separated measurements provide context and help trace the flow of energy through the magnetosphere. Bepi-Colombo completed its 6th and final Mercury flyby in January 2025. The flybys changed the mission's speed and direction and also provided early scientific observations, although many instruments were partly blocked by the stacked cruise configuration. During these encounters, cameras return detailed views of craters, plains, and polar regions. Instruments sampled magnetic fields, particles, and thermal emission. The measurements served both as science and as preparation for orbital operations. The mission's route was adjusted after reduced performance was identified in the electric propulsion system. Engineers developed a new trajectory that preserved the main science goals while moving Mercury arrival to November 2026. As of the middle of 2026, Bepi-Colombo is approaching its complex arrival sequence. The Mercury transfer module is scheduled to separate on September 3rd. The European Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter, named MEO, are scheduled to enter orbit around Mercury on November 21st, and then separate from one another between December 9th and December 10th. Chemical propulsion maneuvers will then place the two spacecraft into their separate science orbits. Routine science operations are expected to begin in April 2027. The nominal mission will last about 1 Earth year and may be extended. Instruments on the European Mercury Planetary Orbiter will map minerals with infrared observations and determine elemental composition with X-rays and gamma rays. They will also measure temperature, landforms, elevation, gravity, the exosphere, and the magnetic field. The Mercury radiometer and thermal infrared spectrometer will examine thermal infrared emission to identify minerals under conditions of extreme temperature. Its global maps are expected to improve understanding of Mercury's iron-poor surface and the origin of its dark material. The Bepi-Colombo laser altimeter will measure surface elevation and roughness. The Mercury Orbiter radio science experiment will study gravity, rotation, and fundamental physics. The spectrometers and images for the Mercury Planetary Orbiter Bepi-Colombo Integrated Observatory System will map the surface at multiple scales and wavelengths. The Japanese Mercury Magnetospheric Orbiter, named MEO, will measure the solar wind before the stream of particles reaches the planet. It will also investigate the bow shock, magnetopores, magnetotail, plasma waves, and energetic particles. By combining data from both orbiters, scientists will study the origin of the northward offset in the magnetic field and the operation of the dynamo. They will also investigate present-day contraction, the minerals of the crust, the development of hollows, the distribution of ice, and the cycle of atoms through the exosphere. They will also observe how the solar wind changes as Mercury moves from aphelion to perihelion. Because the planet's distance from the Sun varies strongly, the space environment naturally passes through different levels of pressure, radiation, and magnetic forcing. Bepi-Colombo is designed not merely to repeat the Mercury surface, space environment, geochemistry, and ranging spacecraft with better cameras. Its purpose is to combine complementary measurements into a more complete physical model of the planet, from the solid inner core to the escaping sodium tail. Mercury is important beyond its own boundaries. It represents an extreme outcome of rocky planet formation. Its metal-to-rock ratio, volatile content, magnetic field, and location near the Sun test theories that must also explain Venus, Earth, Mars, the Moon, and rocky exoplanets. Many planets discovered around other stars orbit far closer to their stars than Mercury orbits the Sun. Some complete a year in only a few days. Their surfaces may be molten, their atmospheres may be escaping, and their rotations may be locked into resonances. Mercury provides the nearest natural laboratory for studying a rocky world under strong stellar influence. It is not identical to those exoplanets, but the physics of irradiation, magnetic interaction, atmospheric escape, tidal evolution, and surface alteration can be tested in detail. The planet also helps scientists examine the boundary between moons, planets, and exposed cores. Some dense exoplanets may be rich in iron, others may have lost mantles through giant impacts or evaporation. Mercury offers one real example against which those possibilities can be compared. Yet Mercury's history cannot be read as a single explanation for every iron-rich world. Its volatile rich surface warns against assuming that high density always means total stripping. Different formation pathways can produce similar masses and radii. Some unanswered questions concern the deepest interior. How large is the solid inner core? What light elements are mixed with iron? Is there a layer of iron sulfide at the top of the core? How is heat transported through the thin mantle? The magnetic field raises further questions. Why is the dipole shifted northward? Has the field always been weak? Did Mercury once possess a stronger dynamo? Are crustal magnetic anomalies remnants of an ancient field with a different geometry? Surface composition remains uncertain in mineralogical detail. Elemental abundances are known better than actual mineral structures. High temperatures, reducing chemistry, and low iron create combinations unfamiliar from common terrestrial rocks. The origin of low reflectance material is still being tested. Graphite from an ancient flotation crust is a leading explanation, but scientists want to determine its abundance, distribution, and relation to other dark compounds. Hollows remain among the most visually distinctive mysteries. What volatile-bearing minerals are being lost? How deep do the source layers extend? Are hollows forming in the present era? And can repeated observations detect change? Explosive volcanic deposits require a source of gas. Which compounds drove the eruptions? Were the volatiles inherited during formation, delivered later, or concentrated through internal processes? Did the timing of explosive volcanism differ across the planet? The age of the youngest volcanic surfaces is another question. Crater counts suggest that volcanism persisted well beyond the earliest heavy bombardment, but exact dates are difficult without samples returned to laboratories. Mercury's contraction may also continue. Small thrust scarps appear geologically young, but their current rate of movement is unknown. There are no seismometers on the surface to record quakes caused by faulting or thermal stress. A future lander could measure ground motion, heat flow, mineral chemistry, and the mechanical properties of the regolith. It could watch the exosphere from below and record micrometeorite impacts, but landing near Mercury is technically demanding because of heat, orbital energy, and communication geometry. A polar lander might investigate permanently shadowed ice, yet it would need to operate in extreme cold and darkness while receiving power from sunlight at a nearby illuminated location. A sample return mission would be even more challenging. For now, orbiters provide the safest and most powerful way to study the planet globally. They can revisit the same regions under different lighting, compare the poles, and connect surface features with gravity and magnetic data. Mercury has no known weather in the earthly sense, but its environment changes continuously. The solar wind rises and falls, magnetic reconnection opens and closes pathways, sodium release varies, dust impacts occur, surface temperatures cycle across the long day. The Sun itself also changes over an 11-year activity cycle. During active periods, flares, coronal mass ejections, and energetic particles alter the conditions around Mercury. Its small magnetosphere responds directly and rapidly. A powerful solar event at Mercury would not produce clouds or rain. Instead, it would compress magnetic boundaries, accelerate particles, increase surface sputtering, and modify the exosphere. The disturbance would be invisible to human eyes unless atoms glowed or instruments translated particle measurements into images. Mercury is also affected by interplanetary dust. Close to the Sun, dust grains have higher orbital speeds, and collisions can release vapor from the surface. Seasonal patterns in calcium and other exospheric elements may be connected with streams of dust, including material associated with comets. The planet's long solar day causes thermal stresses in rocks. Repeated heating and cooling can fracture surface material. On Earth, water and air often assist weathering, but on Mercury, temperature cycling alone may slowly break exposed rock. Micrometeorites constantly strike and melt tiny spots. Solar ultraviolet radiation alters chemical bonds. Energetic ions implant themselves into grains or knock atoms free. Over billions of years, these subtle processes transform the uppermost surface. At human scale, the landscape would seem frozen. At geological scale, Mercury remains under continuous attack from sunlight, particles, dust, and thermal change. It is not inactive, its activity simply follows different rules. Imagine standing safely at the equator shortly before sunrise. The ground would have spent many Earth weeks cooling in darkness. The sky would be black. A faint glow might appear along the horizon only when the solar corona or scattered dust became visible, because there is no atmosphere to brighten the sky. Then the edge of the sun would emerge. It would appear much larger than from Earth, and direct light would strike with enormous intensity. The first illuminated rocks would heat, while nearby shadows remained cold. The sun would climb with extraordinary slowness. A day would not feel like a quick passage from morning to evening, but like a season of light. The landscape would remain fixed beneath a gradually changing angle of illumination. Near noon, the sun would hang high for weeks. Temperatures would peak. No breeze would move dust. No sound would cross open space. Vibrations could travel through the ground, but without air, the world would be silent. As sunset approached, long shadows would spread again. The surface would begin to radiate heat into space. Night would return for another extended interval, and temperatures would fall far below the freezing point of water. At the poles, the experience would be different. The sun would circle low around the horizon. High ridges might receive nearly continuous illumination, while nearby crater floors remained in permanent darkness. This contrast has inspired ideas for future exploration. Sunlit polar peaks could provide solar energy, while robots descend into cold traps to analyze ice. The same region would contain some of the hottest illuminated slopes and some of the coldest permanent shadows within a short distance. Mercury's horizon would curve more sharply than Earth's because the planet is smaller. A person standing on a flat plain would be closer to the geometric horizon. Mountains and crater rims would dominate distant views. The lack of atmosphere would make distant objects appear sharp if dust and local terrain did not block them. There would be no atmospheric haze to soften colors or turn faraway mountains blue. The sun's gravity would shape everything beyond the surface. Mercury's hill sphere, the region where it can hold satellites against solar tides, is relatively small. Spacecraft orbits require careful planning, especially under radiation pressure and gravitational perturbations. Mercury's orbit itself changes slowly over long periods because of interactions with other planets. Numerical models show that its eccentricity can vary, and in some rare simulations the orbit becomes unstable over billions of years. The present solar system is stable on human timescales, but not perfectly rigid forever. Small gravitational interactions accumulate. Mercury, because it is light and close to the Sun, can display comparatively chaotic long-term changes. Most models keep Mercury safely in orbit for the remaining life of the Sun, but a small fraction produce collisions or ejection under extreme future conditions. These outcomes are possibilities in mathematical ensembles, not predictions that such an event will occur. A more certain transformation will come from the Sun's evolution. Over billions of years, the Sun will grow gradually brighter. Mercury's already harsh surface will receive increasing energy. When the Sun eventually leaves the main sequence and expands into a red giant, the inner solar system will be radically altered. Mercury is likely to be engulfed or destroyed as the Sun's outer layers expand, though details depend on solar mass loss and tidal interaction. Long before that distant era, the planet will remain a witness to the Sun's slow change. Its surface contains no biosphere to respond, but temperature, volatile stability, and orbital evolution will shift. The future destruction of Mercury lies billions of years away, far beyond human history, and even beyond the expected survival of most present geological features on Earth. It does not diminish the planet's importance now. Mercury preserves many layers of memory from the inner solar system. Its metallic core records differentiation. Impact basins and volcanic plains preserve the marks of its earliest violent stages. Scarps reflect the planet's cooling, while hollows and the exosphere show that the surface still interacts with heat, radiation, and space. Each trace reminds us that rocky worlds are shaped by starting composition, collisions, internal heat, rotation, magnetic fields, and the transport of material, not merely by their distance from a star. Mercury is often introduced through three facts. It is the smallest planet, the closest to the Sun, and the planet with the shortest year. Behind those simple labels, however, lies a world with a liquid outer core, a global magnetic field, and a faint sodium tail. It also preserves evidence of explosive volcanism, carbon-rich dark material, and a pattern of rotation that can sometimes make the Sun appear to reverse direction in the sky. The planet also demonstrates the value of patient exploration. Mariner 10 opened the first close view. The Mercury surface, space environment, geochemistry, and ranging spacecraft transformed scattered fragments of maps into a globally surveyed world. Bepi Colombo is preparing to continue the story with two orbiters that complement one another. Each mission not only answers older questions, but also raises deeper ones about the core, crust, magnetic field, and material at the poles. Mercury has repeatedly corrected human expectations. It is not locked with one face permanently turned toward the Sun. It is not simply a larger copy of the Moon. It is not magnetically dead, and it was not baked dry in the way early models predicted. The value of the planet lies in these surprises because a theory of planetary formation must explain both common outcomes and extreme cases. From Earth, Mercury still appears as only a small point of light near the horizon, sometimes visible for a few minutes before sinking into twilight. Nothing in that point reveals the long days, the cliffs, the magnetic tail, or the cratered landscape. Yet that faint light has been reflected from a planet racing around the Sun at nearly 47 kilometers per second. When Mercury disappears into the twilight, it does not stop or fade away. The planet continues along the innermost orbit, moving between the evening and morning sky and passing in front of or behind the Sun as seen from Earth. Its year passes quickly, but its day unfolds slowly. It lies close to the greatest source of light in the solar system, while some shadows at its poles never see the Sun. Mercury is the smallest planet, yet it contains one of the largest cores in proportion to its size. It offers the first lesson in the diversity of worlds within a single planetary system. Bodies formed from the same disk of material can still follow separate histories, because even one difference in composition, collision history, or atmosphere can lead to a very different result. From Mercury, the journey will continue outward to Venus, a planet nearly the size of Earth, but wrapped in a dense atmosphere and hidden beneath clouds. An extreme greenhouse effect makes Venus the hottest world in the solar system. The contrast is already clear in the first two planets. Mercury lies closer to the Sun but has almost no atmosphere and swings between extreme heat and cold. Venus lies farther away, yet retains heat beneath an enormous blanket of gas. Between them lies a simple reminder. In planetary science, location begins the story, but it never tells the whole story.